At 9:45 on the morning of November 7, 1940, a steady 42-mile-an-hour wind was blowing across the Tacoma Narrows. It was an ordinary autumn morning on Puget Sound, with no severe storms or unusual weather systems in the area. Standing over the water was a brand-new $6.4 million suspension bridge. It had been open for exactly 4 months, and its design was guided by some of the most influential and respected bridge consultants alive. Yet within 70 minutes, this state-of-the-art structure would tear itself apart in front of a 16mm motion picture camera, leaving behind the most studied failure in the history of structural engineering. The intact deck destroyed itself from within, powered entirely by a steady, moderate breeze. To diagnose what went wrong, the Federal Works Agency convened an elite 3-member board of inquiry, bringing together the leading minds in civil design and aerodynamics to review the wreckage. For decades, introductory physics classrooms have offered a simple explanation for the collapse. The textbook story claims that the wind happened to gust at the exact natural frequency of the bridge, pushing it higher and higher through forced resonance. The investigative board explicitly ruled this out. The wind that morning was remarkably steady. There were no alternating gusts, and therefore no periodic forcing function for the structure to lock onto. Since forced resonance could not explain the failure, the investigators had to look for an entirely unmapped regime of physics to understand what brought the deck down. The search began with the project's macro decisions. The principal consulting engineer, Leon Moisseiff, was a major advocate for deflection theory. The math suggested that the main cables of a suspension bridge could stabilize the structure on their own, removing the need for a deep, heavy stiffening truss beneath the roadway. When the state of Washington balked at the initial $11 million estimate, Moisseiff produced a redesign to save money. He replaced a conservative 25-foot truss with a solid plate girder only 8 feet deep. This chart shows the cross-section proportions of major suspension bridges built up to that point. The previous record holder for slenderness had a depth-to-length ratio of 1:84. With its 8-foot girder spanning 2,800 feet, Tacoma Narrows pushed that, and TL Condon submitted written warnings about the design. They pointed out the unusual narrowness of the 39-foot deck and raised deep concerns over its potential for extreme lateral deflection. The project review board overruled them and approved the construction. The decision was not conventionally negligent. The board was simply applying a mathematically sound static theory past the boundary of historical precedent. Almost immediately upon opening, the bridge exhibited strange behavior. In moderate breezes, the deck would enter a continuous, slow vertical undulation. The motion caused severe seasickness among workers and drivers, earning the bridge the nickname Galloping Girder. Engineers attempted several physical interventions to stabilize the span. They installed hydraulic shock absorbers at the towers, which quickly broke, and anchored heavy steel tie-down cables to the shore, which snapped within weeks. At 10 o'clock on the morning of November 7th, the structural behavior shifted. The bridge stopped moving up and down as a single uniform plate. Instead, one side of the roadway began to rise while the opposite side fell, initiating a severe torsional twist. The deck was rung along its centerline at 12 cycles per minute, reaching a staggering 45-degree angle of twist from horizontal. This transition marked the moment the bridge's movement stopped being a passive reaction to the wind and began to amplify itself, driving toward a total structural failure. The precise tactical cause of this amplification is single degree of freedom torsional flutter. This is a self-exciting oscillation, where a structure, by its own motion, extracts energy from a steady wind to increase its own movement. Because the bridge utilized a solid 8-foot vertical girder instead of an open truss, it presented a blunt face to the wind. As the deck tilted, it acted exactly like a stalled airplane wing. The airflow separated and reattached to the surfaces with a slight delay. Because of this phase lag, the wind applied downward pressure onto the deck at the exact moment it was already twisting downward. This created a negative damping factor. With every cycle, the energy fed into the twist by the wind was greater than the mechanical energy the steel could absorb and dissipate. The structure wasn't just absorbing the wind. Its very shape was harvesting energy from the steady breeze to power its own destruction. At approximately 11 in the morning, the center span finally tore loose. It plummeted 200 feet into the waters of the Narrows, taking a cocker spaniel named Tubby, the only casualty of the collapse, down with it. After months of analysis, the Federal Works Agency inquiry reached its verdict. The collapse was driven entirely by aerodynamic instability, made possible by the extreme flexibility and slenderness of the structure. In their effort to cut costs, the engineers had replaced an open truss with a solid steel web, effectively transforming a massive civil engineering project into a giant airfoil. November 7th forced the profession to permanently recognize suspension bridges as dynamic, aeroelastic structures, rather than passive, static objects simply waiting to be pushed by the wind. The engineers responsible had pushed into a new realm of physics where their existing calculations no longer applied. The math was correct for older designs, but they lacked the vocabulary to anticipate how a radically slender deck would interact with the air. Vertical oscillations had already appeared on the Bronx-Wheatstone Bridge and several 19th century spans. These events were recorded in the engineering literature, but they were documented as isolated failures of cables or stays rather than aerodynamic instability. The findings from Tacoma Narrows established an immediate, permanent mandate. It became inconceivable to design a long-span bridge without first proving its aeroelastic behavior using aeronautical wind tunnel testing. This new standard rippled outward to existing infrastructure. In 1953, the Golden Gate Bridge underwent a massive structural retrofitting to address aeroelastic concerns discovered in the wake of the collapse. The early warnings of the field engineers were correct from the beginning, but it cost a $6.4 million collapse to give the world the physical evidence required to finally understand them.